circle helps us understand. First off, Volkswagen knew that 100 kilogram reduction ends up saving 0.35 liters per 100 kilometers, or in kind of English terms.
Currently, the only participant in the conference.
Do we need to rejoin, or are they listening in some other way?
That's how they're listening in. Otherwise, they're not getting audio.
So we better restart the conference?
We can, yeah.
Oh, if we're the only one, I guess they can dial back in, right?
Yeah, as long as the conference is still going. They're just not dialed in.
And if we're the only one, it must still be going, so
Yeah.
we'll assume we're okay. So a 0.85 miles per gallon improvement, if you're able to knock off that kind of weight. But maybe more importantly is how much NOx, how much of the bad, exhaust we're saving. The thing that presses car manufacturers the most is the improved air quality, the reduction of NOx that they are allowed to push out into the air. Okay? So Volkswagen is very serious about taking all of the weight they possibly can out of the vehicle. Switching to an aerospace example, this is the 787. One of the challenges, just one on that airplane, was to design kind of these ribs for the leading edge of the wing. Okay? And there was 50 of them that they felt like they needed to actually come up with. Why do topology optimization? Well, they wanted to kind of figure out the stiffeners, where the load paths were going to go. They wanted to also look about the integration through all of these stiffeners that they have to put there. They have to run piping. And so the stiffeners need to have some open areas to them. And they wanted to know, could they increase the size of the open area for running the plumbing, the wiring, and everything else that needed to go through those different bulkheads or those different stiffeners to determine the best profile of the part. Boeing also was pressed on doing shape and size optimization. The shape and size optimization was going to push them to reduce weight, improve the stiffness, and an understanding of how the weight displacement moves. These are all things that were written up in their the reports and that they've filed, the white papers that they've filed on topology optimization. So here is this fixed leading edge of the 787 wing. The inboard bulkhead or inboard stiffener is pointed out there, and this was done back in 2005. And what they wanted to do is come up with all of these stiffeners that go on the leading edge of the wing. What was the process that they used? Well, they started out with a design space that was meshed. It was produced in kind of hyper mesh. It was taken in and done topology optimization, and then they had to bring it into CATIA V5 to transform that into some solid representation. They then did a shape and size optimization to figure out, could they thin these members or had to thicken these members? How did they have to actually modify the shape? And then the very last thing that they did is kind of went through this mesh solid back into CATIA. Now going back into CATIA, what happens up here? They have to remodel here, so they're taking this optimization, remodeling it. They go through this path and they get down to hypermesh, and what gets pushed back here? A remodeling exercise. So whatever they've done here on shape and size, they kind of have to push back in and adjust it one more time. So this remodeling is really a problem. So one example, on the left was the best-in-class 777 inboard track rib. Once they did all of the topology optimization for the 787, they came up with a much more open space. Is this better for weight? You would think. Is it better for access? Is it better to push things through these openings than these small little holes in the left-hand part? It's much easier to route pipes and to route wiring and everything else. So this is an example of the traditional best-in-class 777 bulkhead, or not bulkhead, but double track rib. And this is the improved one after they did topology optimization. Why didn't they do topology optimization on the 777? That technology really didn't exist. The only thing that existed was the truss structure, topology optimization. So they could have built this into a truss, but instead of doing that, they just did a traditional, solid metal kind of representation of these stiffeners. With topology optimization, they've been able to come up with much better designs. This graph is what we talked about last time. What are we trying to do? Well, the red line represents the available time, okay? And if you have only that much time and you're coming down using traditional engineering processes for designing your parts, notice that you're not getting enough parts really designed early enough in the system. With topology optimization, Boeing specifically said, we've been able to reduce the design time and push many more parts early on in the development stage. Here's that example again. So the question is, what is today's issue with this? And it really is getting it back into CAD. So that's what we want to talk about, kind of the remaining portion of this period. A student by the name of Shane Larson was one of my grad students a few years ago. And after we did topology optimization in 471, he was an undergrad student, came in and said, I want to look at a technique for trying to get a discretized, optimized part brought more efficiently back into the CAD system. And so this is his research and has been kind of the underlying basis that a number of CAD systems have begun to try and incorporate into their design methodology for reusing or rebuilding CAD. So let's take this simple part as the example. We mesh it, we figure out the design space, we figure out the loads, we figure out the boundary conditions, and we basically ask the topology optimization system to eat away at the part. And so it eats away, and we have to move the slider bar to say, we want this density level, show us this density level, and when it shows us that, we want to then capture that representation and bring it into the CAD system. Okay? So how do we get from that previous image to this? Okay? Well, one of the ways to do that is just export from the topology optimization an IGES file or a step file and bring it into your CAD system. And if you do, you get something that looks very tessellated, very difficult to go in and kind of parameterize and manufacture. So you get kind of these smooth, faceted, type models. What are the common problems of bringing this kind of a part into your CAD system? Well, the first thing is you'll get a bunch of triangles laying on top of each other. Okay? That's just what happens with this topology optimization process. You'll say, I've got two triangles that represent the space. No, I really have one triangle that represents the space, and getting rid of the two that don't represent the space very well is a problem. Okay? It just happens. Another problem is, well, you'll have a triangle that represents the space, and behind that you'll have a rectangle that represents a similar space but laps over into a new space. You'll have triangles that meet at a singularity, or triangles that completely twist around each other, and so you'll get what is referred to as non-manifold topology. So all of these collection of problems exist in the optimized tessellated representation of the object. What you want to do is figure out, how do I get from this IGES representation into my CAD model into something that is fewer surfaces and maybe controlled by parameters that you can actually work with. Well, Shane said it needs to be automated, it needs to be simple, it needs to be parametric, it needs to be a standard, it needs to be, you need to be able to measure the fitness of the shape that's being built. So how do you remember this kind of process? Well, he came up with a way to help him remember this. I don't know whether that'll help you or not, but that was some of his humor in trying to remember simple, parametric, automated, standard, and measured fitness. Okay, so we have this process: topology optimization, geometric conversion, parametric optimization, manufacturing. If we focus on the geometric conversion, we can go in and say, well, there's a manual process that exists. The pros and cons of the manual process is you end up with something that's manufacturable. You can control the complexity, and you have a parametric result. What are the cons? Well, the main one is it's really time intensive. If you walked into Boeing or General Motors or any company doing this, they will tell you the number one long tent pole, the thing that takes all the time, is going from this topology to a real CAD representation. If you look at the mesh refinement approach, you can go in there and reduce the number of points, you can get smooth geometry. The pros are it uses little input and it is repeatable. The cons are it's not parametric. It's difficult to link parametrics to these faceted, smooth surfaces, and it's not a standard model format. There's another research area out there that talks about, well, let's do the topology using a B-spline approach. In this approach, what they do is they take the tessellated model, which is represented on the left, this faceted thing, they pass a bunch of B-splines as section cuts through the object, and then they use those B-splines to actually regenerate a very smooth model. Pretty good approach, pretty good research approach. Pros are manufacturable, model fitness is measurable, repeatable, parametric results. The cons, too complex for subsequent optimization and analysis. So if you're wanting to do shape and size optimization, having B-splines that you have to control are pretty difficult. And little control over the complexity. So once again, his approach was this simple parametric automated standard and measured fitness. And so what he did is he said, how can I take my original object and get from it the point cloud, use section cuts through the point cloud, come up with a way to kind of clock or interpret what these sections should look like. He did it with a polar map. The polar map pulls out any spike is a vertex. And so from the spikes, he was able to come up with the appropriate cross sections and then sweep a solid through the cross sections. So he had a polar map for triangles, rectangles, a regular polygon, and for circles that he was able to do. So again, surface feature selection was kind of his first step.